I would like to measure the spring constant by doing an experiment. If I add this mass to the spring and let it go, it will go down and stop at some point, right? And I want to measure how far it goes down until it stops. It starts from here, when the spring is relaxed, right? So when the spring is relaxed, the bottom of this is at about 35 centimeter. Start from here and then go.
It went to like 35.
35. This is actually 35. It stretches by 1 meter exactly when you do that. Okay, so you start here from rest. It goes 1 meter down and stops there. I want you to think about how we can use this experiment to find what the K constant of this spring is. All right? Half a kilogram mass falls from 35 centimeter to 135 centimeter, and that's when it stops at the bottom. We want to use that information to find the spring constant. So how do we approach that? We want to apply W net equal to delta K. For that, we need two situations, initial and final. Initially, this is this initial situation. You have the spring like that, and the mass is right here. And then when it comes to the bottom point, the spring gets stretched, right? Like that, right? And gets to this point. And the object gets here. This is initial situation, this is final situation. So I draw a line here. I say this is my initial, final. And I have this between these two situations. And I put the y-axis to be able to measure the work of gravity. And this would be like x direction. Of course, these are on top of each other. I draw them separately so that they don't. This is where the spring is connected to the support. Now, what do I know about initial situation? I know the difference of the length between these two is 1 meter, right? So I can say here y initial is equal to 1 meter, and y final is equal to 0, right? 0 of y-axis is here, and this is 1 meter up, right? And then the spring is relaxed at this point. In this equation, when we have W of a spring equal to negative 1/2 K, x2 squared minus x1 squared, x2 is the distance from the equilibrium for the second pole. What is the distance here from the equilibrium?
Meter.
x2, yes, x2 is 1 meter, and x1 is starting from equilibrium, right? So x1 is 0. That's for the spring, right? And what else do we know? What is the speed of the mass here? That would be V initial, right? We said we leave it from rest, right? So VI is 0. When it comes to this point and bounces back at that point,
0.
the V is also 0. V final is also 0. Because it turns around, right? So that makes it easy. All the kinetic energy initial and final is 0. So that says W net is equal to K final minus K initial. But both of these are 0. So this side is 0. The other side is W net. How many forces are acting on the mass? Yes, there are two forces acting on this mass. One is the force of gravity, one is the force of spring. Fortunately, both of these are conservative, and we have formula for their work, right? So W net is W of gravity plus W of spring. And it should be equal to 0 according to this equation. Work of gravity is negative mg y final minus y initial. And work of the spring is negative 1/2 k x2 squared minus x1 squared. That's work of spring. And that's equal to 0, sum of these two.
I thought there was an acceleration. Since it's slowing down.
Yeah, there is acceleration while it's going down. It's pretty much everywhere there's acceleration. But there's no acceleration in this equation. So don't worry about it.
Okay.
Just see what this equation is telling you. It says that net work acting on this object is equal to change of its kinetic energy between any two points that you take. But for convenience, we take that point, this situation, and this situation. And kinetic energy here is 0, kinetic energy here is also 0. So this is all 0, but net work is work of gravity and work of spring. And we have this formula for work of gravity, this formula for work of spring, and according to this should add up to 0. So y final is 0, let's drop this, and y initial is just 1 meter. With this negative, negative becomes positive. Let's call it h now in general. We get negative mg, no positive, mgh for this part. H is 1 meter now. And then negative 1/2 k, x2 is 1 meter, x2 is the same as the height here. So it becomes negative 1/2 k h squared minus 0 squared. Right? Equal to 0. Now solve for k. H is 1 meter. So if you solve for k, one of the h's cancel. You move this over, multiply by 2, divide by h. So k becomes 2 mg over h. But h is 1 meter. And m is 1/2 kilogram. 1/2 kilogram times 2 is 1. Divided by 1 is 1 times g. We will 9.8. 9.8, but the unit of k is Newton per meter. If you follow the units, you see this is Newton, this is meter. It's Newton per meter. So 9.8 Newton per meter because it has the same number as g. Right? So that's k. All right? So it is crucial to draw two pictures, one with initial situation, but with final situation. For the coordinate axis, especially y-axis, so that you can calculate the work of gravity. That's very important. Any questions? So another easier way to measure the spring constant is by using the original force equation. Force of a spring is equal to negative k delta x. See, from this equilibrium point, you hang the mass to another equilibrium point, right? At this equilibrium, the mass is not accelerating. So the forces balance each other. How many forces are acting on this mass?
2.
2. Which ones?
Gravity and the spring.
Gravity and spring. So gravity force is downward, spring force is upward, right? So the force of gravity, which is mg, equals to k delta x. And if we measure delta x now from here, which was 35 centimeter, and then when it is at equilibrium, what is the reading?
That's like 85.
85. So how much is the difference? 50 centimeter, right? So now let's try that one. Say force of a spring is equal to force of gravity. So K delta X magnitude without the negative sign should be equal to force of gravity, which is mg. So K is equal to mg over delta X. What is the mass?
0.5.
0.5. 0.5 times 9.8 divided by, what is delta X? Yeah, 0.5 meters, right? You get what? 9.8. Kilogram meters per second squared divided by meter, or Newton divided by meter. So the same value. Alright? So this was easier, I could do that, but that was more fun. Right? And you see that they both give you the same result.